Welcome to This Explainer. Today, we're diving into a microscopic world of theft and invisible forces that are literally happening right in front of us all the time. We're going to demystify static electricity. We'll look really closely at the tiny, stolen electrons that power everything from your laundry clinging together all the way to devastating lightning strikes. Let's break down exactly how this works, step by step.
So, what could a bouncy backyard trampoline, a towering thundercloud, and a futuristic Van der Graaf generator possibly have in common? On the surface, they seem completely unrelated, right? Well, the answer actually reveals a fundamental law of physics. They can all give you a sudden, surprising electric shock. To understand why this happens in such vastly different scenarios, we really need to uncover the core hidden mechanics of static electricity.
Section 1. Everyday electric shocks. Okay, to understand that spark, we have to talk about insulators. Think of common materials like plastic, rubber, or the fabric of that cozy winter sweater you wear. These are materials that stubbornly refuse to let electricity flow through them. They trap energy. But when two different insulators are physically rubbed together, that simple friction forces something incredible to happen at the very atomic level. It creates a microscopic disruption. Now, the absolutely crucial point here is that only the negative electrons go on a journey. The positive charges, they don't move at all. They remain completely locked in place. Why is that? Well, positive protons are heavy and buried deep inside the dense nucleus of an atom. Electrons, on the other hand, are extremely light, and they orbit swiftly on the very outside. So, when two materials rub together, those outside electrons act as the sole moving pieces in this giant puzzle. They are literally physically stripped from one insulator and forcibly transferred over to the other, entirely because of that rubbing friction. This unequal, unnatural balance of electrons is exactly what creates a static charge.
Section 2. The electron exchange.
Let's visualize this. Imagine rubbing a rubber balloon against your winter jumper. Before the rubbing, both objects are in perfect atomic harmony. They are completely neutral. But friction acts like a microscopic thief. As you rub the balloon back and forth, your jumper gets robbed of its negative electrons. And since it lost that negativity, it's left with an overall positive charge. The balloon, meanwhile, acts like a greedy electron hoarder. It grabs onto those stolen negative particles, leaving it with a strong negative charge. We've literally ripped invisible particles off one object and pasted them onto another. Because of this exchange, a new, powerful dynamic emerges, governed by the electrostatic force. This is a profound law of physics, and the rule is beautifully simple. Opposite charges attract each other, and like charges fiercely repel each other. So in our jumper and balloon scenario, the newly positive jumper and the negatively charged balloon will now physically reach out and attract each other. You can practically feel the tug. But if you had two negatively charged balloons, that invisible force would actively push them apart, completely refusing to let them touch. Section 3. The rules of attraction. So we know opposites attract, right? But how does a charged object interact with something completely neutral, something that hasn't been rubbed or altered at all? Well, this perfectly demystifies that classic magic trick of a balloon miraculously sticking to your head. Let's look at the mechanics. Your hair starts completely neutral, but when you bring that negatively charged balloon close to it, its invisible force reaches out. It pushes the negative electrons in your hair away and pulls the positive charges forward. Because individual strands of hair are incredibly light, the electrostatic force is strong enough to pull those positive charges and the hair attached to them right up to the balloon. It's wild. The balloon attracts a totally neutral object simply by rearranging the charges inside of it. Section 4. Extreme static, lightning sparks. Okay, now it's time to scale up this tiny electron transfer to a massive, deadly extreme. This sequence maps out the sheer, terrifying scale of a lightning strike. And the really fascinating insight here is that it's the exact same mechanism as the tiny spark on your jumper. During a thunderstorm, massive turbulent clouds rush past each other. High up in the atmosphere, ice particles collide. Just like the balloon in the jumper, this vast friction leads to an unimaginably large static charge building up in the cloud. This creates what physicists call a high potential difference between the charged cloud and the completely uncharged ground below. The trapped electrons desperately want to escape to the ground to restore balance. But air is an insulator. However, when the stored charge gets strong enough, it literally rips apart the air molecules. It ionizes the air, temporarily turning a perfect insulator into a conductive wire. The electrons violently flow through this newly forged path, and boom, we experience the blinding light and deafening thunder of a massive spark, which we call lightning.
We can actually test this extreme tension out safely using a school Van de Graaff generator. You've probably seen one of these. A rubber belt rapidly rubs inside the machine, generating a massive buildup of charge on a metal dome. If you touch it while grounded, meaning your feet are connected to the floor, a spark flies. A high potential difference forces a current to flow right through you and safely into the earth. But look at the alternative scenario here. If you stand on a plastic box, which is an insulator, you break the path to the ground. There's no spark. Instead, those hoarded electrons flow directly into you and get trapped. Your whole body becomes highly charged. And because every single strand of your hair now holds the exact same negative charge, they desperately want to get away from each other. They actively repel, pushing apart and standing straight up on end as they try to escape.
Section 5. Invisible electric fields.
To fully grasp this powerful electrostatic force, we need to map out the invisible web that these charges cast around themselves in three-dimensional space. You see, it's a non-contact force. This means it behaves a lot like gravity. It absolutely doesn't need to physically touch an object to aggressively push or pull it. In physics, we visualize these unseen fields using arrows. For positive charges, the arrows point out and away into space. For negative charges, the arrows pull inward, toward them. And crucially, it's a radial field. That just means that the further away you get from the charged object, the more the force dissipates. Up close, the push or pull is incredibly strong and urgent, but as you step back, that invisible web stretches out and slowly fades into nothing. To bring this whole explainer into crystal clear focus, we really have to answer one final fundamental question. Why do we call it static electricity in the first place? Well, the word static quite literally means stationary, or not moving. Insulators trap the transferred electrons, keeping them perfectly still, locked in place, and that allows a massive static charge to quietly build up. Now, if you tried to rub a metal pipe instead, it wouldn't work at all. Why? Because metals are conductors. They're perfectly designed to let electrons easily travel right through them. The electrons would just flow seamlessly through the metal into your hand and escape. That means there's zero stationary buildup, no trapped electrons, no static charge. The whole mystery relies entirely on that stillness. So we've seen how friction quietly steals electrons, how everyday insulators hold them hostage, and how massive potential differences eventually force them to violently arc through the air to find balance. It's pretty amazing when you think about it. Next time you reach out for a doorknob or pull off a crackling winter sweater or jump on a trampoline, take a moment to think about the microscopic journey of those tiny, rustless negative particles. Knowing what you know now, can you spot the invisible forces stealing electrons around you right now?